This is your video for 7.6. 7.6 is over dilations, and let's read this some vocabulary. A dilation is a transformation that changes the size of a figure but not its shape. So since it has the same shape but a different size, that means the pre-image and the image, what you start with and what you end with, are always going to be similar. So we're still keeping with this theme of similarity. A scale factor, we've talked about that word already this chapter, describes how much the figure is enlarged or reduced by. So when we think of dilation, we always think of getting bigger, but you can actually get bigger or smaller. Okay, and one thing I'll just mention here, you're going to get bigger if your scale factor is greater than 1. You're going to get smaller if your scale factor is between 0 and 1. So 1/2, 1/4, 1/3. The negatives do something else, and we'll talk about that in class tomorrow, what a negative scale factor does. But for now, we're just looking at, is it a big number, bigger than 1, or is it a small number, 2/3, 3/4, something like that, smaller, between 0 and 1. For a dilation with the scale factor of k, you can find the image of a point by multiplying each coordinate by k. So dilations are super simple. If you have the coordinate 2, 3, once you know your scale factor is 2, you just multiply it. 2 times 2 is 4, 2 times 3 is 6, and there's where your new coordinate is. It's super simple. Okay, this section 7.6, it combines what we've been doing with chapter 7, proportionality, similarity, those kind of things, with what you did on your project, your transformation project, because you did reflections, rotations, and translations, and now the fourth one is a dilation. So we're kind of combining chapter 7, proportionality, similarity, with chapter 12, transformations. Okay. The figure shows the position of a JPEG photo. Draw the border after a dilation with a scale factor of 3/2. So this is really easy. A is at 0, 0. So when we multiply by 3/2, nothing happens. A is still at 0, 0. So you don't have to do that one ever. We do have to do the other ones. So let's look at B. B is at 0, 4, so I'm multiplying by 3/2. Of course, this is still going to stay 0. I should be doing this. 4 times 3 is 12. 12 divided by 2 is 6. So this one, we're going to call that B prime, is going to be at 0, 6. Then let's move over and do D. D is at 0, 3. So that's still going to be at 0. 3 times 3 is 9/2 for D prime. So this is going to be D prime. Oops, I did that backwards, didn't I? I'm a dork. D, how about D is at 3, 0? It doesn't really change the answer. There we go. Sorry. So this is at 9/2, 0. Now with C, we could go and do the same thing, but we already know what the answer is going to be. We already know that the x coordinate is going to be at 9/2, and we know the y coordinate is going to be at 6. So then there is the drawing with the scale factor of 3/2. So you can see it's kind of stretched out from the origin, moving this way, and everything's just gotten bigger. I pulled it taller and wider, so we have a dilation there. Okay, given that triangle AOB is similar to triangle COD, find the coordinates of the scale factor. Find the coordinates of D and find the scale factor. So since we don't know what D is, we're going to focus on this side. And this one is super simple, but I want to show you the procedure for when these get a little more complicated. All you have to do is divide the coordinates onto one another. So 0 divided by 0, that's going to be 0. That's not going to show you anything. But the 4 divided by 2, you're going to get 2. So that means your scale factor is 2. Everything is getting twice as large. So since B is at 3, if everything is getting twice as large, then D is going to just be at 6, 0. So this one is a really, really easy case, but just imagine this would be the same thing if these coordinates were 3/2 and 4, or anything weird like that. Okay? Alright. Example 3. Given the coordinates of these triangles over here, prove that triangle ABC is similar to triangle ADE. Okay, so proving triangles similar is really easy. We just use their side lengths and we compare them and we see if they're proportional. The same way as if I gave you two triangles and all their sides, you would just divide them out. Only on the coordinate plane, we have to figure out the lengths ourselves. Now, because these triangles share this angle A, we only have to prove two sides because we're kind of going to use our side angle side thing. So we use side angle side in chapter 4 to prove triangles are congruent. We can use it again to prove that they're similar. So if I can prove AB is similar to AD, and I can prove AC is similar to AE, then I've got the side angle side thing going for me. So here we go. Let's find the distances of these four pieces that I'm interested in. So from A to B, we are going to go up 2 over 2. So that's square root of A, which reduces to 2 square root of 2. I have AD. 1, 2, 3, 4. 1, 2, 3, 4. So I have 4 squared plus 4 squared. 16 would be 32. Should be 4 on the square root of 2. Okay, I'm going to move over to the other side over here for AC. Is 2 and 1. So that is square root of 5. That doesn't reduce. I'm still going to move this over here just so that all my final answers are in one line. And AE. Let's see, 1, 2, 3, 4. 1, 2. Let's see, 16 and 4 would be 20. Okay. So now we need to compare. So I am going to divide AD by AB because I'm just saying that we started with AB and we're headed to AD. So I want to see what happened when I got there. So I'm going to divide the big one by the small one just to make things a little bit easier. So that would be 4 on the square root of 2 divided by 2 square roots of 2. Square roots cancel out and I get 2. Same story on the other side. AE is the big one over AC is the small one. And it wouldn't matter which way you did this as long as you kept it consistent. Oops. So square root of 2 divided by 2 square roots of 5 divided by square root of 5. Those cancel out and it just leaves you with 2. So since these have the same similarity ratio, and the angle in the middle is congruent, that means these triangles are going to be congruent. So I prove I prove triangle ABC is similar to triangle ADE. Now you need to check your scale factor because this is one thing that's a lot of you messed up on the quiz before semester break. It's got to go in the same order. So from ABC to ADE, I'm going from a little triangle to a big triangle. So that's an enlargement. And like we talked about on the last page, if I'm getting bigger, I want a scale factor that is going to be bigger than 1. If I had written this statement backwards, I could just as easily say triangle ADE is similar to triangle ABC. And I would be going from a big triangle to a small triangle. That would be a reduction. So his scale factor would be 1/2. It would be as if I flipped these over. So I would get a number smaller than 1. So that's something you need to be very careful about. That's the most missed thing with scale factors, is giving you the wrong way. Here, small to big is an enlargement, so a big scale factor. Here, big to small is a reduction, so a small scale factor. Alright, last one. Graph a triangle with the vertices 2, 3. Ignore the dogs. I try to. B is at 0, 1. And C is at 3, 0. dilate the triangle with a scale factor of 2. So we learned last page on the other side of the note, super easy to dilate. If they're given the scale factor, you just multiply everything by that. So A is at 2, 2, 3. I just multiply everything by my scale factor of 2. So A prime is at 4, 6. So here's A prime out here at 4, 6. Same story for C. C would be 1, 2, 3 more places. C prime would be at 6, 0. And B prime would be at 0, 2. So there is my new triangle. It's twice as big because the scale factor is 2. And here I'm dilating, and I always am going to be dilating for this, for geometry, at the origin, which means everything's stretching out from the origin. So you can see it's just getting twice as far away from the origin.